If it's a municipal water supply, they don't want to do that. They want to leave the water where it's at because they've got customers that are clamoring for the water.
Welcome to the Ground Investigation podcast. In this episode, we'll be joined by Scott Anderson, a seasoned geotechnical engineer specializing in numerical modeling and risk-based analysis for critical infrastructure projects. We'll explore modeling benefits and pitfalls, engineer training, and the power of risk-based design. Sounds like your kind of episode? Hit like now so more engineers can find this conversation. Scott, welcome to the show.
Well, thank you for having me.
Well, thank you for giving us your time. So could you walk us through your geotechnical journey from early beginnings to now being a national voice in modeling and risk-based infrastructure work?
Okay, well, I've got a rather convoluted path to engineering. I started with a music degree nearly. I have 3 years of a music degree, performance in trumpet, before I was 17.
Mm-hmm.
And after that, I didn't know what I wanted to do. My dad was a professional musician, and so I knew what that life was like, and I realized I did not want to do that.
Yeah.
And so I didn't know what I wanted to do, so I joined the military. And so I was in the military for a total of 8 years. And then as I was getting out, I was married to my first wife, and she was a civil engineer. And she said, "You really ought to try engineering." And I said, "Oh, no, I can't do that. That's much too difficult." And she said, "No, just take a look at my books and see what you like." And I just happened to pick up the geotechnical books and said, "Wow, this is really interesting. It's part art, part science. And it's got geology to it, which is just something I really enjoy." And so I started school at University of Kansas initially, took a ton of geology courses and was really looking forward to, finishing my bachelor's degree and going on to my master's. And so then I happened to get divorced and transferred schools to University of New Mexico. Well, they immediately said, "What did you take all that geology for? It doesn't count for anything here." And so I finished up my bachelor's in 1995 at University of New Mexico and went on to start studying for my master's and PhD there, and got all my coursework done and just kind of gave up on it. And moved back from University of New Mexico back to Kansas and started with a geotechnical firm there called Geosystems Engineering, which is long since gone. But they hired me as a technician initially because they said, "Well, you have a bachelor's degree. We don't hire bachelor's degree people except for as technicians." And so I got a lot of experience on the back of a drill rig and at project sites. I did lots of that work until one of their engineers decided to leave, and they said, "Well, heck, Scott's nearly got his PhD, so why don't we just have him start writing reports?" So I started doing that, and about 10 or 12 years into it, I went back for a master's degree in geological engineering and mining engineering from University of Missouri-Rolla, and then that leads me up to where I am now in terms of my degree. But I've kind of bounced around from place to place. I was with Kleinfelder for 17 years, and then HDR for 9 years, and then a few smaller firms for a while, and then I wound up at Wheeler, where I'm at now, as of the first of the year.
Struggling to find top geotechnical and geoenvironmental talent? You could use a generalist recruiter, or you could use a specialist. At Geo Expert Search, we place experts where they belong. Across the UK, USA, Australia, and New Zealand. No highways, no bridges, no structures. Just geotechnical and geoenvironmental. Now and forever. Geo Expert Search. Finding the right people for the right roles with no wasted time. Visit geoexpertsearch.com to learn more.
Excellent. So that's quite the journey then, isn't it? From going from potentially becoming a musician into the army, And then it's obviously, geotechnical engineering, which you're into now. So numerical modeling is double-edged sword, powerful, but easy to misuse. What should geotechnical engineers watch out for?
Well, like they say, all models are useful or dangerous. Some are more useful than others. Um, Numerical modeling, while it can be very beneficial to a project, is something that shouldn't be undertaken lightly because, one, it's a very costly type of analysis, or it can be, especially for my work in dams. It can be particularly costly because we have to do usually a seismic deformation analysis, which is what I tend to do a lot of. When I do numerical modeling, it's a rather costly process, and it could be dangerous if you don't know what you're doing. It goes everything from your field work to your parameters that you select from your field work and your lab work, all the way through your analysis, where you start simple and you move towards more complexity in your analysis. Because some people jump in and they want everything in the kitchen sink in their analysis, all this detail and everything else, and then they can't tell what's causing what in the analysis. They put in a retaining wall and the specifics of the piling supporting a retaining wall or something. And they didn't start from simple and go to complex. They just started with complex. And then they wonder why they have a certain problem with it not converging to an end of an analysis.
Okay.
Then you have simpler numerical models like limit equilibrium for slope stability, simple finite element for seepage, although seepage analysis can be quite complex in itself, especially for 3D, which I've done 3D seepage analysis and stability analysis for large dams like Oroville. We did a 3D seepage and stability, and it can take a lot of time, even for those type of analyses, given that sometimes dams' internal zonation is very complex, and putting that into a model right off is just wrong. You have to build in things bit by bit by bit, and then you can verify your analysis step by step that you're getting something that makes sense, not just creating a pretty picture, which a lot of people see a numerical analysis and they go, oh, wow, look at that. It produced a stress contour map and it looks really nice. Well, it may be totally wrong. If you're doing a dynamic analysis, you have to start with a static analysis, and your static analysis has to be solid before you move to the dynamic analysis. Your obliquity ratio in your dam has to be within a certain range, and everything has to line up so that when you do your dynamic analysis, things will actually work.
Yeah, I was just kind of looking on my phone as you were talking, because we had a fellow on called Yichi Do, so it's episode 31 if anyone's particularly interested in numerical modeling, but we had a whole 45 minutes to an hour, specifically on the technical side of it as well. So it's an interesting topic, and it can get quite complex, kind of numerical modeling, once you start chasing it down.
Yes, it can. And it's a fun thing to do because you get to do all sorts of interesting computer work. And I started playing with computers when I was a kid, and it's just kind of followed me throughout my career. I ended up getting a certificate in computational science along the way while I was working with massively parallel computers at Sandia National Labs, which was a lot of fun, where we took finite element code and turned it into parallel finite element code for chasing some rather complex problems.
Excellent. So modeling wins or horror stories, let us know your experience in the comments wherever you listen to this too, or perhaps watch it on. You can watch it on YouTube also. Scott, so you're known for mentoring. What does excellent training look like today for young engineers?
Well, the first thing is to get them out in the field, get them experience with the built environment, whether it be, structures, doing concrete testing, doing bearing capacity checks out in the field, being on a drill rig and seeing how we come up with all the samples and everything else. That's where it starts. Unfortunately, we get a lot of times where someone comes out with their PhD in numerical modeling and they don't want to do the field work. But that's something that I think we as employers really have to kind of stick to our guns and say, you really do need this. And then, mentoring can come kind of quite naturally from water cooler talks, talking about projects that you've had in the past, letting them, explore, your mind essentially, about what you've done in the past, how you approach things. You have to give them room to fail too, and try things and not worry about, consequences necessarily right off. You have to let them, kind of flounder a little bit at it and let them come to some conclusions and let them use their critical thinking skills to attack a problem, provide prompts, to that problem. That's the kind of mentoring I tend to do. And I try to use what I call servant leadership, or what's been termed servant leadership, where I'm there to help them progress in their career. I'm there to show them the path to where they want to go. And it's important that, as employers, that we ask our employees, where do you want to be in 5 years, 10 years? What do you see yourself doing? And then make that possible for them. That's where I see, and then just providing them opportunity, to do that kind of work, and slowly progress them along. That's my idea of mentorship.
Excellent. And that's a good idea of mentorship as well. You need to, see where their mind's gone. Like I said, I suppose it's a little bit like parenting in a way, isn't it? You have to let
it is
fail a little bit in order for them to learn themselves, because you can read things in a book when you actually feel rather than are told. It's a kind of different feedback, I suppose, for the person. Risk-based design has grown in influence. How do you use risk-based analysis to steer big decisions in geotech?
Well, a lot of what I do is I've been trained as a facilitator in semi-quantitative risk analysis, and I've performed several fully quantitative risk analyses through my career on large dams. Most notably participated in the Isabella Dam QRA and the Scoggins QRA, the fully quantitative risk analysis, where we take the dam and look at all the potential failure modes for the structure. And this can be done in a design or in, an existing structure, like I do a lot of the time, where you look at all the potential failure modes and then you run them through logic trees to find out where, those failure modes land in terms of what's called an FN diagram for people who are experienced in it. And it just plots the probability of failure versus consequence along the bottom axis. And we look at these FN charts and look at the societal potential for, or not potential, but societal adversity to risk, which is about 10 to the minus 4 or 10,000, 1 in 10,000 years. Anything above that line essentially says you have a rather serious problem and you need to be doing something about it to fix it. And as the consequences increase, that line also there's a diagonal line that goes down. So as the consequences increase, you also have that line dropping. The coal to fix it is sometimes incurred at a lot lower potential for failure. So we use that to help the owner of the dam to prioritize what they're going to try to attack first. So anything above that line, of course, they immediately have a call to, do something. And then if they have a portfolio of dams, you can do semi-quantitative risk analysis or a screening risk analysis. and you can look at a portfolio of dams and say, which dam needs the attention more than the others? Or say, you have several dams and you can look at your capital expenditure program and say, we're going to put so many dollars towards this or this or this because of the results of the risk analysis. It helps also with design. When you're designing say a new tow drain project for a dam. As you can see, most of my experience is in dams, so I draw on that a lot. But for like a tow drain, say you're putting one of those in and you have to cut the slope back and everything else, you can run through a PFM or potential failure modes analysis to look at all the construction risks that you might be facing, and look at doing things differently because of those construction risks, and staging things differently, say doing a tow drain slightly more shallow and putting a buttress over the top of it so that you don't have to draw down the reservoir as far during the construction event. Sometimes with dams, you have to draw the water down, and if it's a municipal water supply, they don't want to do that. They want to leave the water where it's at because they've got customers that are clamoring for the water. So you have to look at risk to their potential for not servicing their customers as well. So there's lots of interesting bits and pieces to risk. Doing landslide risk analysis, looking at landslides and how they affect the public and economics too. If a road gets closed because of a landslide and things like that. So you can apply risk to a variety of projects. My experience has mainly been in dams, though.
Okay, so on that subject of the candidate risk, can you walk us through a project where modeling and risk made a real impact, which I'm sure you could come up with many?
Oh, Isabella Dam, where the auxiliary dam is on the distal end of a alluvial fan. And of course, that is a potential for liquefaction there with loose sands and silts and things. And so we did a lot of numerical modeling to feed into the risk analysis. And of course, you can't run every possible scenario. So you have to be very selective about what you're doing so that you can cover essentially all the ground motions between a 475-year event all the way up to a 9,975-year event, or even farther if you're dealing with Bureau of Reclamation. They do 50,000-year events sometimes. And so you have to be able to kind of hopscotch your way through all the different ground motions that you have to apply, and then also possibly doing a parametric analysis of different material properties in certain layers. And you can see just from talking about, a bunch of different ground motions and a bunch of different parameters you want to change, that can really exponentially, just go crazy about how many analyses you need to perform. And, it's something that we had to do for Isabella Dam. We did probably on the order of 100 different analyses for looking at the different liquefaction characteristics of that alluvial fan and other materials in the dam. And then there was the whole fact with the Isabella Auxiliary Dam that there was a conduit through the whole thing, which was rather massive. And they didn't know how it was constructed. They didn't have any as-built for it. And so that's another risk that we had to consider. And also the fact that you get stress rotation around sharp re-entrant corners, and that can also cause cracking in dams. When you get the flip-flop of the sigma 1 versus sigma 3, it can create a low stress zone that is susceptible to cracking or hydrofracture as well, when you're drilling in the dam. But Isabella Dam was one we did just massive amounts of modeling that fed into the risk, and it became evident to us that it was going to be a major rehabilitation project, And haven't been involved in it for about 15 years. I did this way long time ago, and they just finished the rehabilitation last year, I believe.
Long-term project then.
A very long-term project.
Does it ever affect how you sleep? Because obviously if you work on projects that big, there's so much at risk. Obviously you've got the public factor of safety in there as well. Do you ever kind of stay awake at night thinking, did I check that one? Did I run that one correctly in as many times as I should?
Quite a lot, unfortunately. You lose sleep sometimes and you go, well, I want to run that again. I want to check that just to be sure. Doing all the checks up front helps me sleep a little bit, but it still runs through your mind at night.
Yeah, it sounds like it would. Is there kind of another question from that? As there's so many kind of different methodologies which you can use, I suppose at some point you have an analysis on which analyses to kind of go ahead and use as well, do you?
Well, for the most part, we use FLAC, which is programmed by Itasca, because it's probably the most well-recognized program to do nonlinear deformation analysis or seismic deformation analysis, because it's well proven and it's been used, so many times. Whereas a lot of people will use Plaxis or Diana or, any one of a number of programs, but FLAC tends to be the one that I use most and I'm most familiar with. Although they've added in a lot of features to it now that I'm getting older and it's harder for me to learn.
Okay, talking about the kind of geotechnical software modeling there, and then AI as well. What do you think's coming next in terms of those things?
Well, I think a lot of machine learning type of projects are really kind of coming to the fore. The MPM method for run out of large deformations, where you couple FLAC analysis to I always mess up the acronym, but it's MPM, and it does particles. And so you tie those two analysis together, where FLAC runs it down to where it can have a large geometry error and stop. And then you use MPM to take the momentum from that and run it out. And you can get an actual, deformation like, Jack Montgomery is using it a lot at Auburn University. And they also, Kenji Soga, I believe, is using it at Berkeley. There's quite a few academics that are really into it, and it's really starting to become something that might be able to be used in practice with some people, who have done their PhD in it or their master's work in it. Could bring that to the fore in practice. AI is come up a lot of times in my own use of it. I use AI a lot for report writing. It works out really well when you want to word a paragraph in several different ways, and you're not sure which one sounds the best. And so you tell it to rewrite the paragraph 5 different ways in a professional tone, and then you can pick and choose sentences that you want to use. Now, I wouldn't have AI design a foundation for me or a dam for me necessarily. I might ask it to, give me suggestions on things, and see what it comes up with. Sometimes it comes up with rubbish.
Yeah,
it's,
it does.
But it's a tool that as long as you understand the limitations of it and the implications of it, it can be very useful. LinkedIn has given me a kind of a path towards finding other people who are interested in machine learning and the use of it in analyses, where you can teach it a particular way of looking at something. It'll look at it in its own way based on the data that you have, and you can try to validate that against something that is a built structure, say, and look at it and see how well it does at validating a deep excavation using machine learning or something like that.
Okay, what advice do you give to young engineers trying to build a meaningful career in geotechnical engineering?
Oh, just learn all that you can. I think no matter what university you come from, some people are very elitist and they say, well, if you don't come from a certain university, you didn't get a good geotechnical education. Well, I really kind of put that back on the person. You've got to take interest in your own education and your own learning. And, after university, you're going to be out on your own to a certain extent. You're going to be guided by mentors, but you've got to put stock in your own learning and really take that to heart and look for things that you're interested in, look for a field you're interested in, try things out. I always liked what the Army Corps of Engineers used to do when they got a new graduate and place them in different offices and doing different things, field work, office work, and everything, and let them experience different, aspects and see what they want to do. And I think it's incumbent now that, not everyone goes into the Army Corps of Engineers, but that you kind of take that upon yourself as a young graduate to try to experience as much as possible and see what you like and, try to build a career out of that.
I remember when I was at university and I was studying geology, the contact hours initially were 16 and then it went down to about 6 in the final year. So really the education was really, it come down to you. You would have the support, guidance and mentorship of the lecturers, professors, that sort of thing. But really the people who'd done the best, they took all ownership of it, because 6 hours a week of lectures compared to how many other hours a week you have to study and everything else. It definitely comes down to you. It's the same as a career as well, isn't it? If you just wait for opportunities and you perhaps won't go as far, you have to go and make things happen yourself. The same with many things in life.
Exactly. And if you find yourself in a position, that you've hired on to, and you don't think that it's going to be fulfilling as a career, try it for a little while, but if it doesn't fit, look for something else that does fit. Take the opportunities, when they come along. Not for money, but for learning. Money is nice, but if you're not happy in your job, then you're going to be miserable.
Yeah, you soon get used to. I was speaking to someone the other day, and we just kind of got on a really good pay rise into another company, but I was really clear. It says the additional money, you'll get used to very quickly, and you'll just adapt how you live. But the other things provided, that's the things for growth and support and everything else. Money,
exactly.
Money, just as long as you don't have a problem with money, and like you don't have hardly any money at all, that's the only real time. But beyond a certain amount, you're kind of all right. You might just kind of change your lifestyle around a little bit, buy a fancier car, maybe live in a slightly different house. But beyond that, it doesn't make you happy, unfortunately. So, Scott, thank you for your time and knowledge and the passion that you bring to our profession. Do you have any final thoughts before we sign off?
Not really. I just would like to thank you for the opportunity that you provided. And I, hope that young engineers will listen to this and hopefully get something out of it.
No, they certainly will do. Each guest brings a kind of, their own experience to the show, really. So there's lots of different things from lots of different guests. So if you're listening to this and you haven't listened to them all, please go back and listen to a few. Perhaps pick out the ones that you like the titles of initially and see where it takes you. So this wraps up another Ground Investigation podcast. Like, comment, and share if this episode gives you insights. And make sure to subscribe and never miss an expert guest like Scott Anderson. Scott, thank you very much for your time.
Well, thank you.